Okay. Okay, ladies, gentlemen, and B, welcome back to Prague Non-Commutative Geometry and Topology seminar. Today's speaker is Nicola Ciccoli from Università di Perugia, and he will talk about orbit correspondence and groupoid sister algebras. Please, Nicola.
Okay, so thank you for the invitation, for this opportunity. Of course, it would have been much nicer to be in person, in presence, but we will have some other occasions, I hope, and we will just try to get the best possible from the situation. So when I discuss the topic of this seminar, I like to start with this slide that I already used sometimes, because I found that this citation is very interesting. It's by David Vaughan, which is maybe one of the biggest experts in representation theory of Lie groups. And talking about orbit method, in fact, this comes from a review of a book by Alexander Kirillov, which is considered to be the standard reference text for orbit method. He's saying that for him, orbit method is a kind of damaged treasure map, offering cryptic hints where to find some, but not all of the things we're looking for. And I like this because really orbit method is a method. It's not just a bunch of theorems, like saying under certain circumstances, some objects do correspond. It's more like there is a general philosophy that some geometric data that are labeled, generically speaking, as orbits, and we will see a little bit more about that, are related to some algebraic data, which are generically labeled as irreducible unitary representations. But a lot of different features may appear in this correspondence. We will only discuss some of them, and it's more like physics situation than mathematics, because what happens is like a physical phenomenon. You have certain perfect conditions under which you see it in full glory, and that's importantly groups. And there are a lot of different situations in which some of the features appear and some others do not. And so you sort of use examples as experiments to detect where some features are appearing of the orbit method and when not. And I think it's a very interesting situation, and this treasure map can sort of keep you engaged for a lifetime, if you wish. So we will try to explore a part of this map, and a part of the map that is usually referred to as quantum orbit method, because it has to do with quantum groups and quantum homogeneous spaces. I don't like at all this name, even if I use it because it's commonly used in literature, but I found it a bit deceiving, because orbit method in a way is something inherently quantum. It has already quantization built in. It's just that instead of doing it in the linear case, you're doing it in a quadratic case, or if you wish, in a non-linear case. So the real name should be something like non-linear orbit method, when you're dealing with quantum groups instead than dealing with Lie groups. And I will explain what I mean in a second. So this is the classical situation of orbit method, which, as I said, for me it's already, or if you wish it, quantum orbit method. You have some way of quantizing the general Poisson manifold. And for the moment, I'm not going to detail about quantization procedures and the outcome that I want to have at the end of your quantization procedure. Just say that some non-commutative associative star algebra that quantizes your Poisson manifold. And what you call this quantum orbit method is trying to set up a correspondence between the set of symplectic leaves of your Poisson manifold on one side and the set of irreducible unitary representation of this algebra on the other side. So that's what you call a quantum orbit correspondence. Now, the example, the easy example, the classical orbit method is the one in which you start from a linear Poisson structure on the dual of Lie algebra. So your Poisson manifold is the dual of Lie algebra G with its linear Poisson structure that's determined by the Lie bracket on G. And then you consider its universal enveloping algebra as a form of quantization of this linear Poisson structure, which you may see as by saying that the graded associated algebra to the universal enveloping algebra are just polynomial functions of the dual. And in fact, then you see that symplectic leaves on the side of this linear Poisson structure are the same as coadjoint orbits. So this is very classical, and this is where the name orbit method comes from. And then you set up a correspondence between coadjoint orbits in G star and the star irreducible representation of the universal enveloping algebra. And then you know that these are connected to irreducible representation of the Lie algebra, which is the object you really want to study. So you say you want to know something about the irreducible representations of G, and you look at this in coadjoint orbits. That's the classical orbit method. As I was saying, this is very well behaved when you're dealing with nilpotent Lie groups. This is quite well behaved when you're dealing with solvable Lie groups. In fact, what are called exponentially solvable Lie groups are again a very nice setting. This is not so easy to discuss and detect when you're dealing with semi-simple Lie groups, but still it's interesting also in the compact case or semi-simple case in general. In fact, there is an even simpler case. You start with the zero bracket. So it's even simpler. Whatever quantization procedure you want to consider, you expect to end up with some algebra of functions on the manifold that say you consider the sister algebra of continuous functions. And then you know that this correspondence between symplectic leaves, which are points of the original Poisson manifold, if the Poisson bracket is 0, and star irreducible representation of the algebra of functions is just a Gelfand transform. You know that you can, in fact, let's say the correspondence is given by considering the kernel of irreducible representations, which are primitive ideals in the algebra of functions, and modding out by them, you recover points. And in fact, here you see that, of course, it's not very interesting to say that two sets are just in bijective correspondence. The point is that here you can recover the topology of M from the Jacobson topology and the set of primitive ideals in the sister algebra of continuous functions. So this correspondence allows you to recover the topology of the original Poisson manifold. An example which maybe you know, maybe not, it's more interesting from our point of view, is the standard compact Poisson Lie group. So let's call K a compact Lie group. There is a Poisson Lie group structure that's called standard, which is the one underlying the usual quantization of compact Lie groups. And so that, let's see, you can build up this quantum function algebra, this non-commutative quantum function algebra. Of course, you can consider it as usual via generators and relations, and then complete it to a sister algebra or by some other procedures. And here the point is that, again, you have a nice relation. Symplectic foliation on the side of the compact Poisson group is given by so-called dressing orbits of the action of the simply connected Poisson dual K star on the Poisson group K. And you can study the set of star irreducible representation of the corresponding quantum group. And Soiberman at the beginning of the 90s showed that, in fact, these two sets are in bijective correspondence. As I was saying, he said something more interesting than just a bijective correspondence. He showed that both such sets are associated to some combinatorial data that you can attach to the right group of K. So basically classified dressing orbits and classified star irreducible representations, and showed that they were classified by the same kind of objects that are some combinatorial data that you can build from the Y group of K. And so it's not that you just have a correspondence, is that you know how to pass from a dressing orbit to the corresponding irreducible representation and back. Let me say in principle. Then in practice, it may be much more difficult, but in principle, you know how to pass from one to the other. In his results, there is no mention about topology of the spaces. So, of course, I mean, when I say topology, it's clear that on the left side, you can consider the quotient topology. You have a Poisson manifold, you have the set of leaves, and you just consider the quotient topology, the set of leaves. On the other side, it depends on, let's say, really the algebra of functions you're considering. If you, as I will do in the following, consider a sister algebra quantization, then at the sister algebra level, you have Jacobson topology on the space of primitive ideals. So you have a reasonably defined topology on the set, let's say, at least of primitive ideals. And I will discuss a little bit more about this later on. Let me show also an example in which you have a hole in the map. I mean, we said that this treasure map is a little bit old. There are some holes in it. There are some areas in which you don't know what happens, or maybe you don't know what happens. So let me show a case in which things are not working very well, or maybe yes. So consider the case of a sympletic structure on a torus, left invariant with respect of the translation of the torus on itself. These are classified by a real number, and you choose this number to be irrational. And whichever quantization procedure you can consider, this has been done in a lot of different ways, in a lot of different, I think basically this example is a sort of test case for all possible quantization procedures. You always end up with, or you expect to always end up with the C-star irrational rotation algebra, the quantum torus. And well, since the starting manifold was symplectic, you have on the side of the symplectic foliation just one point. But it's known that the problem of classifying star irreducible representation of the quantum torus is a so-called wild classification problem. So basically, you have no hopes to classify them all, and in any case, they are infinitely many. Okay, so at least you can say that for sure there will not be a bijective correspondence. So this is a case in which you feel like you need to understand something more. Now, in a way, this is the introduction part, and let me discuss the kind of quantization that I want to consider, because, of course, some of the things that I've been discussing are very much dependent on the quantization procedure that you want to consider. So I will consider quantization, so-called quantization via symplectic groupoid, and I will explain a little bit what this means. Of course, I cannot go into all details. This is a quantization procedure that was introduced in the late 80s. It's funny because it was introduced by 3 different people in 3 different places at the time, not communicating very much between them. So Karashev in Soviet Union, Alan Weinstein in Berkeley, and Stash Zakshevsky in Warsaw. And they both came up with the same idea of using symplectic groupoids to quantize Poisson manifolds, relying on geometric quantization of symplectic manifolds. This procedure, I will describe it in more details later, was sort of dormant for 20 years, and there is a reason because it was dormant. There are some steps which are very difficult and were not solved at the time, and then was revived in a very nice paper by Eli Hawkins in 2008, and that's basically will be sort of the setup in which I will move myself. And the outcome of this procedure is what is called the groupoid sister algebra. So the sister algebra associated to a groupoid. In fact, in some cases, it's a twisted groupoid sister algebra, where this twisted refers to twisting by a tuple cycle, which will appear very vaguely in the following. And as I was saying, this relies on classical geometric quantization procedures. And there is a nice part in this that you have a lot of geometric data involved in your construction, line bundles and connections and whatever. And then there is a bad part in this, is that all this construction depends on the number of choices that you're making along the way. And you have a very weak control on what happens if you change choices. So you have to sort of have faith in the fact that at a certain moment you will do the right choices, or that for some reasons the outcome is invariant with respect to these choices. But there are really few theorems stating that quantization is, for example, invariant under change of polarization. So let me outline a little bit this procedure. These are just the steps, and then I will go into detail in the steps. The first step is what is called sympletic integration. You start with a generic Poisson manifold, and you want to build up a so-called sympletic groupoid integrating it. Now, I never know how much is known about this when I speak to an audience, so I will give some examples and details later on. If you know what I'm talking about, to any Poisson manifold, you can associate a Lie algebroid, and then you have a reconstruction theorem that says something like, more or less like, for Lie algebras, you can integrate to a Lie group. Also for Lie algebroids, you can integrate to a Lie groupoid, okay, under certain conditions. And in some cases, you can have a symplectic structure on this groupoid. And that's what you're looking for. So this will be step one. You will start with a Poisson manifold, you construct a symplectic groupoid. Then you have to choose a polarization, and you have to choose a Lagrangian fibration. Polarization means a Lagrangian fibration of your symplectic manifold. And this Lagrangian fibration has to verify certain compatibility relation with the groupoid structure. So this is what is called a multiplicative Lagrangian fibration, and this multiplicative properties implies that the projection to the set of leaves is a groupoid morphism. So I'm saying two things: that the set of leaves has a natural groupoid structure, in fact a topological groupoid structure, and that the projection is a groupoid morphism. And then you know that in geometric quantization, you have to take into account holonomy of Lagrangian leaves. And so you have Bohr-Sommerfeld conditions appearing. I mean, if the topology of the leaves is non-trivial, you have Bohr-Sommerfeld conditions appearing. So here you have to show that under some additional geometrical constraint, your multiplicative Lagrangian fibration ends up in selecting topological subgroupoid of Bohr-Sommerfeld leaves inside the groupoid of Lagrangian leaves. Looks like a lot of steps to do. And finally, you have this Bohr-Sommerfeld groupoid, which is a topological groupoid. Then you cross your fingers, and if everything was nice, you have enough structure to build the groupoid sister algebra associated to this topological groupoid. And that's what you call the quantization of the original Poisson manifold. And I will try to convince you, if you have never seen this before, that in some cases you already know all these 4 steps and you have seen it before. So there is some dust under the rug in this procedure that I've chosen not to mention too much. That's the prequantization step. So the prequantization step was fully understood in a paper by Alan Weinstein and Ping Xu in the beginning of the 90s, and I will assume that my Poisson manifolds are all prequantizable, and it's in this prequantization step that the groupoid Tuco cycle may appear. And I will assume trivial groupoid Tuco cycle so that the resulting sister algebra is not twisted. This fact that the groupoid Tuco cycle is trivial relates to properties of the Poisson cohomology class of the original Poisson bivector. The problem is it relates to it in a very subtle way. So there are some cases, and these are the cases I will talk about, in which this Poisson cohomology class is non-trivial, but still the groupoid Tuco cycle is trivial. But let's say generically speaking, Poisson cohomology class non-trivial should be equal to non-trivial groupoid Tuco cycle, but it's not exactly so. And I think that no one has really understood up to now actually why in some cases this the groupoid cycle is trivial, even if the Poisson cohomology class is not. There are many subtly different cohomologies that you can consider in this situation. So that's one of the points. So what is this integration step? Let me now sort of enlarge a bit the picture and go step by step into what I was discussing. What it means integrating a Poisson manifold. It means finding a groupoid, which has to be a Lie groupoid. A Lie groupoid has two maps. I mean, your original Poisson manifold should be the unit space of the groupoid. So you have source and target map that will go from the total space of the groupoid to the Poisson manifold. There should be a symplectic form on the groupoid. It verifies this multiplicative condition that I've not written in detail, but that's compatibility between the symplectic structure and the groupoid structure. And this implies that the source map is a Poisson map. So you have a Poisson. Let me remind that source and target in the Lie groupoid setting are both surjective submersions. So you have a surjective submersion, which is the source, that's a Poisson map to the Poisson manifold, and the target, which is an anti-Poisson map to the Poisson manifold. Okay, so you have these two natural. In a way, this can be considered some sort of desingularization of your Poisson manifold. Now, this was the step that blocked the field for 20 years because it was not known which Poisson manifolds were integrable. And then Krajnic and Fernandes in the, I think, beginning of the 2000, like maybe 99, maybe 2001, I don't remember exactly, showed that there is a specific Poisson invariant that you can compute and tells you if the manifold is integrable or not. And let me say that in most cases that you usually deal with in quantization, this is always possible, okay? But I've written this vague, almost always possible, that takes the place of writing down which is the Poisson invariant that you should compute to understand if your Poisson manifold is integrable or not. But in principle, you can check if your Poisson manifold is integrable or not. The explicit integration is often very difficult. We are just lucky that in the setting of Poisson Lie groups and Poisson homogeneous spaces, it is not so difficult. But it took some years to understand how you could proceed. But in general, for a generic Poisson manifold, finding an explicit symplectic groupoid integrating it is often very difficult. So this is usually the most difficult step. Nice part of this procedure is that symplectic leaves of the original Poisson manifold correspond to orbits of the Lie groupoid. So you know that whenever you have a Lie groupoid on the unit space, you have orbits, and these orbits are exactly the symplectic leaves of the original Poisson manifold. And now mentioning a famous paper on Hopf algebras by Majid, I want to convince you that everybody knows what a symplectic groupoid is. And that's if you take a trivial Poisson manifold, the pi equals 0, the bivector, then you just consider its cotangent bundle. This is a symplectic groupoid with Liouville symplectic form on the total space and source equal target equal to the bundle projection. And so this is the easiest possible case of symplectic groupoid integrating. The cotangent bundle is a symplectic groupoid integrating the zero Poisson structure on the base. Now, second step is choice of polarization. Now, let's see. Okay, I will discuss the case of real Lagrangian multiplicative polarizations. Of course, you can consider real polarizations or scalar polarizations like in geometric quantization. A real Lagrangian multiplicative polarization on a symplectic groupoid is an integrable Lagrangian distribution, which verifies these two properties. This M is the multiplication of the groupoid that goes from the pairs of multiplicative elements to the total space of the groupoid. The inv is the inverse. So you have these two conditions that are relating either the Lagrangian distribution or this symplectic orthogonal to let's say, the multiplication and the inverse of the groupoid. And they're not very transparent written down like this, but I haven't found a nicer way to write them. Of course, I could cheat a lot and say, okay, if you know something about the algebraic groupoid, a real Lagrangian multiplicative polarization is what is called the wide sub-LA groupoid of the tangent groupoid of the symplectic groupoid. A little bit too many groupoid in this phrase, but that's what it is. And multiplicativity is the condition that guarantees that the set of Lagrangian leaves is a quotient groupoid. As I said, there's a topological groupoid with a projection, which is a groupoid morphism. Problem is, real Lagrangian multiplicative polarizations does not always exist. In fact, they usually do not exist. I mean that even if you consider the Poisson-Lie group structure on SU2, you can show that there is no real Lagrangian multiplicative polarization of its symplectic groupoid. There are topological obstructions. So you need to allow singularities, but in a way, this is no surprise. This is what happens even if you are doing geometric quantization for the harmonic oscillator. If you want to take a real polarization, you need to allow singularities. And here it's the same. You need to allow singularities, and there is a way to define generalization that I avoided because it would have been a couple of slides to mention which kind of singularities are allowed in such a way that the projection is still a groupoid vibration. And we did this together with Francesco Bonecchi, Jean Q, and Marco Tarlini in a paper, well, it's already 9 years ago. And it's connected to the idea of building an integrable system on a symplectic groupoid. Now, so this was the step of the choice of Lagrangian polarization. And as I said, there is no guarantee that different choices of Lagrangian polarizations will end up in the same quantum sister algebra. That's a problem, and you don't know what to do about it. When Lagrangian leaves are not simply connected, the existence of what are called covariantly constant sections along the leaves is not guaranteed. So you need to have some topological condition that selects usually discrete subsets of Bohr-Sommerfeld leaves, and the condition is trivial holonomy. And again, in this paper with Francesco and the others, we showed that there is a way to give geometrical conditions. I mean, they're expressed through cohomology of the leaves that guarantee that the Bohr-Sommerfeld subgroupoid, so that the set of those Lagrangian leaves that verifies the trivial holonomy condition is a topological subgroupoid of your original groupoid. And so in this way, you end up with finally this groupoid of Bohr-Sommerfeld Lagrangian leaves, in which we've done two steps, starting from the original symplectic groupoid. One was a quotient, and the other is taking a subgroupoid. This is a bit weird because in a way these two things behaves functorially in a different way, in different directions, taking a quotient and taking a sub-object. And this is maybe responsible of some of the weird aspects of quantization from the functorial point of view, at least in this setting. And then there is the technical step on how you construct a groupoid sister algebra when you have a topological groupoid. I will take for granted that in our cases this will be possible. You have to fix what is called the left R system and on your topological groupoid, and then you can construct the groupoid sister algebra. But under, let's say, rather mild condition, at least mild in this setting, you usually can construct this groupoid sister algebra. I will give a couple of examples. And this is what you call the quantization, okay? Which seems a lot of work to reach something, but that's how groupoid quantization behaves. Yes, Alessandro?
Nicola, yeah, there is a question from Karen.
Yes, sorry.
if they are ever et al, I guess the groupoids.
Yeah, in our cases, yes. Okay, so the cases that we discuss about always end up with the tile groupoid. But I don't think that in general you can say that there is some general theorem telling you that in a generic situation you're bound to end up with a tile groupoid. But all the cases I will show gives you a tile groupoid.
Okay, thank you.
Oh, sorry. Okay, so let me first say about the trivial case. So for simplicity, say compact manifold with zero Poisson structure. As I said, the symplectic groupoid is the cotangent bundle. So here things should be easy. You can choose as multiplicative Lagrangian polarization just the vertical polarization. So your Lagrangian leaves are the cotangent spaces. Okay. And therefore, the space of leaves is the original Poisson manifold. All leaves are vector spaces, so they are simply connected. Therefore, there are no Bohr-Sommerfeld conditions. You don't need to impose Bohr-Sommerfeld conditions. So, as I was saying, the space of leaves is just the original manifold in which you have a trivial groupoid structure. So every point is a unit and you don't have isotropies around. So when you build up the corresponding groupoid, sister algebra is just the algebra of continuous functions on the manifold. If it was not compact, it should be compactly supported continuous functions. And that's what you wanted. Okay, your quantization is the sister algebra of continuous function when you take the zero Poisson structure. And of course, you know that Gelfand transform in this case tells you that in fact you can reconstruct the unitary dual. From the unitary dual, you can reconstruct your original topology on the manifold. Well, less trivial case, standard symplectic space, R2N. So with the standard symplectic form. So here the Poisson bivector is the inverse of the symplectic form. The symplectic groupoid is R4N with the pair groupoid structure and the standard symplectic form. So you have many possible choices of real multiplicative Lagrangian polarizations here, and you can choose the horizontal one, for example, and you have all leaves are simply connected again, therefore there are no Bohr-Sommerfeld conditions to impose, and you show that what you end up with is that the resulting sister algebra is the sister algebra of compact operators on L2 space on R2N. Okay. Here the groupoid structure is non-trivial because you're starting with a pair groupoid. And here you have Neymark's theorem that takes the place of what tells you that the quantum orbit method holds true. The unitary dual of compact operators is 1 point. Okay. You started with a symplectic manifold, you end up with 1 point on the quantization side, okay, the unitary dual. Now, I put this slide because I once gave a talk about this to someone that did not know very well about groupoids. So this is maybe a remark, but just to remember that you can see a groupoid as some sort of bundle in which you have orbits on the unit manifold and you have isotropy groups let's say on the fibers, and this isotropy group, the isomorphism class of the isotropy group is constant along the orbits. And then what happens is that the isomorphism class may vary even widely when you're moving transverse to the orbits. So a good approximation is to think in terms of orbits plus isotropies is what sort of builds up the whole groupoid. And as we said, orbits are symplectic leaves of the original symplectic foliation in the symplectic groupoid. It's not the same when you go down to the Bohr-Sommerfeld. So let me see. Okay. So now let me say this. Now we're going into some details, and some of them are a little bit dense, but the idea is the following. Now, I want to understand this orbit correspondence. So let's say that I can do all this groupoid quantization. I start with a Poisson manifold, I end up with a groupoid sister algebra. And I want to relate the symplectic foliation, the topology on the space of leaves on the geometric side with the unitary reducible representations of my groupoid sister algebra. So I need some technical instruments, or at least I need some math to understand irreducible unitary representations of groupoid sister algebras. There's no way around it. I mean, I need to know how to relate irreducible unitary representations of the groupoid sister algebra to the groupoid itself. And this is where orbits and isotropies pop up. So say you have a generic topological groupoid and you take an element in its space of units and you take an abelian subgroup of the isotropy. Then you can consider a representation of this abelian subgroup. And then there is a well-defined induced representation of the groupoid sister algebra on a certain Hilbert space. That's Hilbert space completion of compactly supported function on the isotropy group, tensor the Hilbert space you started with. This is what he called the induced representation in the context of groupoid sister algebra. And this is the main tool that you use to build up a correspondence between irreducible representation of groupoid sister algebra and its orbits, or if you wish, its orbits plus isotropy. Sorry. This was introduced already by Riffel, basically. And the point is that here you have an action of the group on the unit space. And you can move this action also to representations of the isotropies. Since points in the same orbit have isomorphic isotropies, each time you have 2 points on the same orbit, you can move from one point to the orbit to the other, and from one representation of its isotropy to another representation of the isotropy of the other point. And you can show that basically this action does not change the result. So if you start from 2 points on the same orbit and related representation of their isotropies, you end up with the same irreducible representation of the groupoid sister algebra. The easiest case in which all isotropies are abelian, which is the one we will mainly discuss about, which, well, you need some additional assumptions. So say your topological groupoid is locally compact, second countable, and all its isotropies are abelian. Then you can show that if you start from an irreducible representation of the isotropy group, then the induced representation is irreducible. You can show that, as I was saying, there is this action of the groupoid itself on its orbit, that moves from one induced representation to another in such a way that the two representations are equivalent. So if you have an element gamma in the group that moves from U to U gamma, so you can multiply the unit U with gamma, then you can build up another induced representation that will sit on the point source of U gamma, and the two representations will be unitary equivalent. Then, of course, you can mod out the set of units by the groupoid itself, and you build up a map from orbits of the groupoid to unitary dual of the groupoid sister algebra, and in general, this map is injective. If the orbit space is Hausdorff, then this map is also continuous. In fact, it's continuous in under much weaker hypothesis than this, but just as a first step to remind that the separation properties of the orbit space will play a main role in the following. But on the other hand, if the orbit space is not even T0, then the sister algebra is what is called the non-postliminal sister algebra, and therefore you have two different sets, primitive ideals and unitary reducible representations. And this is what happens for the quantum torus. That if you, well, I should go in detail. I will go in detail in an example that's related to the quantum torus, and I will show in a few minutes. But if the orbit space is not T0, then you have sort of to consider this fact that your quantum orbit method will fail, because on the side of, let's say on the target side, you should not look for irreducible unitary representations, but for primitive ideals. Now you have a condition that's very interesting, under which you can understand a little bit better the topology of the full unitary dual. That's in this case, so when you have a amenable et al. Hausdorff groupoid, Hausdorff referred to the total space, and then this construction that for any closed invariant subset of the set of orbits, the restriction of the groupoid is what is called topologically principal, which means that this restriction has trivial isotropy on a dense subset. Then the corresponding sister algebra is always a type 1 sister algebra, and the induced representation map is always a homeomorphism. But a homeomorphism, when on the left side you have to consider what is called the quasi-orbit space, and it means that this is more or less the same as the space of orbits, but you need to identify two orbits that have the same closure. Okay, and we will see that in a case that we will consider this is enough to conclude something interesting, but in another case this is not enough, because we will have many different orbits with the same closure. So this is a, let's say, technical setting under which you know that this you have a nice correspondence between a geometric object related to orbits and the unitary dual. So let me come back to the original question. I wanted to say I'm quantizing a Poisson manifold, and I want to know if the quantum orbit method holds true under this quantization procedure. So let me first stay in a nice part of this treasure map. And I will consider Poisson-Lie group structures on the three-dimensional Heisenberg group. And here the Poisson-Lie group structures were classified, I think, already at the beginning of the 90s. They can be described all explicitly together with their symplectic foliation. And there is a natural way to define the quantizing sister algebra. This was done, much of this work was done by B.J. Kang in 2000, between 2003 and 2008. It's 4 or 5 different papers, but the two main ones in 2005 and 6. And you can show that, in fact, the quantum orbit method in this setting holds true perfectly well. You have that the irreducible representation of the unitary dual of the sister algebra with Jacobson topology is homomorphic to the space of leaves of the Poisson manifold with quotient topology. And last year, I wrote some brief notes in a review paper that all this can be reconstructed using symplectic groupoid quantization, because in this case, the symplectic groupoid as a symplectic manifold is simply the cotangent bundle. The groupoid structure is twisted by the Poisson structure in a way, but basically you can write down things in a very explicit manner and recover this result under the setting of groupoid quantization. Now, why was the quantum torus part not working? So, as I said, I will describe this in a slightly different example than the quantum torus, which is a bit more interesting and I want to discuss. So consider we have a k-dimensional torus with the right invariant symplectic form. I do not want just to consider it as a symplectic manifold, but I want to consider what are called toric manifolds sometimes. So I will consider a manifold with a smooth torus action, and I will move the Poisson bracket, the Poisson symplectic form on Tk to a Poisson bracket on M in this way. I will consider on the Cartesian product the Poisson bracket given by 0 Poisson on the M part and the symplectic form on the torus. And then I will mod out by the diagonal torus action, which acts on the right on M and on the left on TK. And it turns out that this always induces a Poisson structure on M, because of course this quotient on the right of this arrow is M itself as a manifold. But the Poisson structure on M cross TK induces a non-trivial Poisson structure on the quotient, okay, in which basically the orbits are all tori, eventually of lower dimension than K, if the group action has some isotropy. An example of this is by considering a very natural T2 action on the 3 sphere, and you get the Poisson version of what is called Conlandi-Matsumoto 3 sphere. I mean, it goes under different names. It appeared in a paper by Conlandi, in an older paper by Matsumoto. I think Piotr Ayats also did something on these, or together with some collaborators. I mean, it has been studied and rediscovered a number of times. But it's a Poisson structure on the 3 sphere. In a second, we will see its Poisson foliation. And already in the work of Eli, the geometric quantization of the groupoid quantization of this Poisson structure was quite explicitly described. The symplectic groupoid as a symplectic manifold is just a cotangent bundle, but source and target map will not just be the projection. Still, you can write down an explicit real Lagrangian polarization. These Bohr-Sommerfeld conditions are partially non-trivial. Basically, these Lagrangian leaves are of the form S1 times R2, so you have some conditions on holonomy. And what you end up with is that your quantization sister algebra is the sister algebra of an action groupoid. You can consider an action of Z by irrational rotation on S2. I mean that it acts on irrational rotations on parallel circles on S2. So that's why I called it an horizontal action. Okay, just consider, decompose your S2 into parallel circles, and then you have an irrational rotation action on those circles. And this gives you an action of Z on S2, and you consider the sister algebra associated with this action. This is a generalization of what you can do with the torus. I mean, the quantum torus, in which here you would have Z acting on S1. Here you have Z acting on S2, decomposed into a family of S1. And the space of orbits here is not zero, the space of orbits of this groupoid. So you expect that the unitary dual is different from the primitive ideals. But you expect to recover the symplectic foliation in terms of the primitive ideals, and this is what happens. Let me remind that in the case of the quantum torus, you have only one primitive ideal. So the quantum orbit correspondence for the quantum torus holds true if as target space, instead of considering the unitary dual, you consider the primitive ideals. Here's something similar happens. You can consider this quasi-orbit space is just the interval -1, 1. And inside here, you will have two orbits which correspond to -1 and 1 on the sphere. They correspond to the north and the south pole of the sphere that have non-trivial isotropy. All the other orbits have trivial isotropy. Then there is a sister algebra theorem that's called disintegration theorem that tells you that whenever you have some closed invariant subset of the orbit space, you have this nice decomposition sequence that tells you that the full groupoid sister algebra decomposes in terms of its restriction to X and its complement. And here you can use it to show that the Poisson foliation that is written on the left hand side of this diagram corresponds to the primitive ideal space. In this way, you have, as I was saying, a Poisson structure on the sphere. The corresponding symplectic foliation is given by two circles of zero-dimensional leaves, and then a whole bunch of tori that glue together into solid tori. So you have to expect that all the points corresponding to t greater than 0 are glued into a solid tori, and all those corresponding to t less than 0 are glued into another solid tori, and the two solid tori are glued together by interchanging the two generators of the torus, this red circle that I wrote in some of this tori. I mean, that's what is usually called the ergod splitting of the sphere. And this is the Poisson structure. And in fact, this reflects very well on the set of primitive ideals, where you can show that the set of primitive ideals is an interval, but with an additional z attached in a way to the t equal 1 and t equal -1 points. And this z of points sits in the closure of t less than 1. And when you go to t equal 1, you go in the closure to all points of this. Sorry, I said the z, a circle attached to this t equal 1 point. So it's like you have a cylinder, and you mod out by an equivalent relation that identifies parallel circles on the cylinder at all level except for the top and down level. And this is the topology that you end up with in the quotient. That's a topology on the space of leaves on the Poisson side. That's also the topology on the set of the Jacobson topology on the set of primitive ideals. So you see the symplectic foliation just with the primitive ideals, not with the reducible unitary representations that have some geometric meaning, but that we will not discuss. And now finally to the examples that I wanted to discuss with you. That's the case of this family of covariant Poisson structure on the projective space. This is, there is a one parameter family of Poisson structure on CPN that are covariant with respect to the standard Poisson-Lie group structure on SUN. They depend on this parameter. When t equals 0, 1, they are called standard. When t is in the interval 0, 1, they're called non-standard. And they're all, sorry, here there is a mistake in the slide. I wrote Poisson quotient. The standard one are Poisson quotients. Well, it depends on what one means with Poisson quotient. Okay, so they're quotient of standard Poisson-Lie group structure on SUN. So you have the standard Poisson-Lie SUN, and then you can take quotient either with respect to Poisson-Lie subgroups, and you will end up with the standard ones, or with respect to what are called coisotropic subgroups, and then you will end up with the non-standard ones. Their quantization can be realized as quantum homogeneous spaces of classical quantum group SUQN. They're all star subalgebra and say right coideals inside the classical SUQN. They were introduced as such by Deikoisen and Stockman in the 90s. Okay, they can be given explicitly by generators and relations. In those papers, generators and relations are explicit. In the standard case, the quantum orbit relation is known to hold. This was proven by Stockman in the late 90s, but also, I think I misspelled the Neshveyev, right? By Neshveyev and Tuzet, because they showed that each time you're modding out a Poisson-Lie group by a compact Poisson-Lie group by a Poisson subgroup, quantum orbit method holds true, and they do it in some sort of, let me say, in the Seubermann setting, by which I mean that they classified objects and they show they relate, but they keep track also of the topology. So the result is a homomorphism, in fact. So it can be considered as a big refinement of Seubermann results. Now, those cases are interesting because here you can build this groupoid quantization. This was the main topic of our work of 2013. You know the n equal 1 case, the Polish sphere. And I wrote the two Polish, the two cases of standard and non-standard Polish spheres. And from the point of view of the Poisson geometry, the standard Polish sphere, you have a 0-dimensional leaf and the complement, which is a 2-dimensional leaf. In the case of the non-standard Polish sphere, you have a circle of 0-dimensional leaves. I wrote it as the equator, but it's just a parallel in general. So you have a parameter t that's telling you at which height you have this S1 of circles, and then its complement are two symplectic leaves. And the level of sister algebra quantization, in the standard case, you see that the sister algebra quantization is just a minimal unitization of compact operators. So compact operators are corresponding to the big two-dimensional leaf, and then you add the copy of C that correspond to the zero-dimensional leaf. And in a non-standard case, you have two copies of compact operators that are glued together by an S1, basically. So the two copies of compact operators are playing the role of the two open leaves, and the S1 is gluing them together. These non-standard CPN are generalizing this situation. The symplectic foliation is much more involved, and we will see it in a second. So,
sorry, Nicola,
yes.
What about the case t equals 0? What is the?
What about, sorry?
You said that also the case for which t equals 0 is called standard. What does it correspond to?
Sorry, I missed the case. So you can say that t equals 0 and 1 is either the North Pole or the South Pole.
Oh, I see. Okay.
That was the question. And this is t equal 1/2. So that's the typical, I mean, the parameterization I'm used to consider these two cases in this way. 0, 1, and 1/2 is the equator 1. Okay, but of course you can make some changes in the parameter and whatever.
Okay, thank you.
So what about the standard case? In the standard case, I mean, for the general complex projective, from the Poisson point of view, you have one cell in each even dimension. And the topology of the space of leaves is that each cell sits in the closure of the higher dimensional one. I mean, maybe I should have written n instead of n+1, but okay. So you have exactly as for the Podley sphere, where you have one symplectic leaf in dimension 0 and one in dimension 2. When you go high with the dimension, you have 1, 0, 2, 4, and so on. And the closure relation is very easily described. And here you are in this case in which you have the singular multiplicative Lagrangian polarization. You have non-trivial Bohr-Sommerfeld conditions. This groupoid satisfies those hypotheses of Simpson-Williams that I wrote before. And from there, you compute explicitly the unitary dual, and you can show that quantum orbit method holds true, exactly as you would expect. As I said, this is proven in a different way by Neshpeyev and Puzet, so we are happy to recover the same result. Let me say one thing I'm cheating about a little bit. It's not in principle, it's not at all obvious that with groupoid quantization, you obtain the same thing that you obtain with quantum groups quantization. Okay? And proving that the two things are the same is not easy. Of course, you can tell it afterwards when you have the full set of irreducible representation and say, okay, these two sister algebras are the same. Nice. But if not, it's not so easy to say that the two things, the two objects are the same. In a way, the generators of the groupoid are not very well behaved with respect to generators and the relations. Let me put it like this. Now the non-standard case. This is something I'm working on. It's more or less complete, but still not completely finished. And as I was saying, these can be seen as quotient of SUN by coisotropic subgroups. So not by Poisson's subgroup. You have to conjugate a little bit your Poisson subgroup, and you obtain a coisotropic subgroup. You mod out that, and the quotient by a coisotropic subgroup is always a covariant Poisson manifold, and you find this different Poisson structure on the quotient. In quantum homogeneous spaces term, you can find them as infinitesimal invariant with respect to a coideal subalgebra of the universal enveloping algebra. Okay, and this is the general principle that this coisotropic subgroup at the level of the universal enveloping algebra should correspond to coideal subalgebras. In this case, neither Stockman or Neshpeyev two-set results apply because they are for Poisson quotients. And here again, you can compute this groupoid quantization and the singular Lagrangian multiplicative polarization and the corresponding BS groupoid. Here again, so Karen will be happy. It's et al. It's amenable. It's topologically principled with abelian isotropy. So this also tells you that the corresponding system algebra is post-liminal, so you do not have the problem of having two different possible target spaces, unitary dual and primitive ideals. But it's topologically principal, but restriction to closed invariant subsets are not topologically principal. So these results by Sims and Williams does not apply. You have to take into account this non-trivial isotropy that correspond to the fact that you have S1 family of symplectic leaves in the foliation, and not just like the S1 family of zero-dimensional leaves in the case of the non-standard polished sphere. Now, I don't want to be too much long, but let me say, let me skip this slide, and this is a paper.
Nicola, sorry, there is another question from Karen.
Oh, sorry. Yes.
She says probably already mentioned this, but in this principal et al. Case, what is the Cartan subalgebra?
No, I haven't mentioned this. I don't know the answer immediately like this. I have to think a little bit about it. Sorry.
Okay, okay, thank you.
Maybe we'll see it. So there is a result which is a little bit technical, but very recent. This goes back to August last year, so 5-6 months ago, by Van Wyk. I don't know the pronunciation, if it's Van Wyk or Van Wyk, and Williams, that consider the case in which you have abelian isotropy with what they call continuous isotropy except for jump discontinuities. Okay? And in this case, they have an explicit homomorphism between a certain set that they construct explicitly and the unitary dual. And basically, you see the set they start with are pairs, an element in the unit manifold and an element in the unitary dual of the isotropy, modded out by a certain relation given by an action of the groupoid. And then you also have to consider what I call the T-zeroization of the certain topological space. And sorry. Now, just a couple of words about, here there is a misprint, about the groupoid in a non-standard case. It's I will describe its unit space. Okay, its unit space is made up of pieces that I write down as delta Rs for when R plus S is between 0 and n, that are done in this way. These are triples, A infinity B, where A is in ZR, then you have n minus R minus S copies of infinity, and then B is in ZS. So there should be a comma here. With this relation that I plus 1 is greater or equal to AI, greater or equal to a certain fixed number. So this CTQ is a fixed number. And similar relation with the BIs, this mainly tells you that this A can go to infinity, and they go to infinity, let's say, the A is from right to from right to left, and the B is from left to right. Okay. So you can add up some infinities inside here, taking away the numbers here and here. And this gives, in a way, takes into account the closure relation. The topology on this discrete space is such that this delta ij sits in the closure of delta rs when I is less than R and j is less than S. And the unit space basically can be divided into two subsets, those delta that correspond to R plus S exactly equal to n, and those that corresponds to less than n. And in a sense, this is the regular part and this is the singular part. The regular part is open and dense, I mean, on the set of units, and the isotropy over the regular part is trivial. The singular part has non-trivial isotropy. I wrote S1 because I wrote this slide too much in a hurry. The isotropy is Z. And of course, its unitary dual is S1. And you can show that this jump discontinuities property of Van Wyck and Williams applies. So you can use the result, to show that in fact, with this tool, you can show that quantum orbit methods hold also for non-standard complex projective spaces. And just to give a little bit more details on how the symplectic foliation and the result is done, in the N2 non-standard case, with this disintegration theorem, you have this decomposition sequence in which you have 3 copies of compact operators that correspond to 3 big 4-dimensional leaves. And then you have the singular part sitting here. So you can say that your full complex projective spaces is gluing these 3 4-dimensional leaves with some singular subset, and the singular subset are 2 copies of S3 that are glued together along a copy of S1. Okay, sorry. So this S3 is the usual quantum S3, I mean, the one that you can construct from SUN. So at the Poisson level, its symplectic foliation is the symplectic foliation of SU2, is the quantum SU2, if you wish. Okay. So you have 2 copies of SU2, of quantum SU2 glued together along a copy of the 0-dimensional S1, I mean the one with trivial, the commutative one, the one of characters. And this is the singular part. And then you have 3 4-dimensional leaves that glue together to form the whole CP2. This, of course, is just the n=2 case, but the general case is not very different. Okay, so what I was saying in words is written down here. And of course, you can follow very well that which is the closure relation. And yeah, okay. So basically, you can show that here you have all the information about this symplectic foliation. And a case that I mean, this is in preparation. I'm still writing it. The case I really would like to understand is this case. That's the case of what are called 3-dimensional Poisson-Stokes matrices. The Poisson bracket is, I mean, you are in R3. The Poisson bracket is x bracket y is equal to xy minus 2z, and then you have cyclic permutation of this. So you can write yz and zx. And this has a Poisson group interpretation. It's not a Poisson quotient of SU, this should be SU2, but it's a Poisson quotient, sorry, SU3, but it's a Poisson quotient of its dual. Okay, and it's a quotient by a coisotropic subgroup. And the symplectic groupoid is known, in fact, since the work of Bondal in 2008. The topology on the leaf space is very nice. It's T0. You have a Casimir function that is this very nice function. And so you have that the Poisson foliation is given by level sets of this Casimir function. Of course, you have a very specific value of this Casimir in which you have 0-dimensional leaves. But generically, the leaf is 2-dimensional. But the reason why it's very interesting is that in this case, you have coexistence of simply connected and non-simply connected leaves. And non-simply connected leaves is where something interesting happens, because whenever you have a simply connected leaf, in the symplectic groupoid, you are sure to have, you're bound to have non-trivial isotropy, and which will survive also at the level of Lagrangian polarization. So you will have a bigger coisotropy group. And it would be interesting to understand, in a way, this is something similar to the case in which you're doing orbit method for solvable Lie groups, when you have to take into account orbits plus an additional data that comes from the fact that orbits are not simply connected. While in the nilpotent Lie group case, all the orbits are simply connected. So here you have, it would be nice to have an example. Together with Fabio Gavarini, we showed that this can be easily, this can be described at the quantum group level with no problem. So as an algebra of coinvariants, So you have all, basically you have all the ingredients, but I still don't know the answer. And that's all. Sorry if I was maybe a bit long, but thank you very much for your attention.
Thanks, Nicola. All right. Is there any question or comment?
Yes, I see a raised hand by.
Yeah, there is yes, please, Branimir.
Hi. So can you please go back to the slide with the about the Conlandi spheres for a second?
About, sorry,
the Conlandi spheres.
Yes.
I have a question up there.
Yes. Yeah, that was it.
Yeah, just before this, just the general setup one. So in general, in this kind of setup, does one get that the groupoid C-star algebras are the theta deformations of M?
Yes.
Okay. Okay,
Yeah.
because one point I was a little confused about was the relation between, for instance, in this case, this groupoid C-star algebra and the usual S3 theta, because S3 theta isn't a straight up cross product by this rotation. It's a sort of Kunz-Pimsner construction where you have basically a topological line together with the rotation.
I think, I mean.
So I don't know if is there a Morita equivalence with the usual plate cross product?
No, I mean, I think that. So I think it's actually the same as when you show that the quantum torus written with generators and relation is the same as the quantum torus that you obtain as cross product of Z over S1. Sorry. And so they're not really Morita equivalent. This is really the same sister algebra. And I think this was already in the work of Matsumoto. If I've understood your question, I'm not completely sure.
So this cross product is just the literal cross product just by the rotation.
Yes.
About the north-south axis.
Yes.
This naked cross product, unless there's some weird Morita equivalence going on, this won't give you back S3 theta on the nose because that it's non-cleft. You really have this non-trivial line bundle together with the rotation. Like S3 theta is generated over S2 by not just the rotation, but there's this non-trivial line, basically the tautological line or its dual, twisted on the one side by this rotation.
Okay, no. Yes, I think now I got a little bit better your point. Yes, so this, maybe you're right, this you can show that in so what I have in mind is this. This should be, in fact, I think you're right, it's a Morita equivalent, and that should exactly reflect the fact that you can describe the Conlandi three-sphere in two ways, starting from groupoid quantization, choosing two different multiplicative Lagrangian polarization. And you show that the different choices of multiplicative Lagrangian gives you two different Morita version of the same algebra. Okay, let me.
Okay.
And I think your remark is a very interesting one because this should be connected to the fact that that the prequantization level you could choose a different way of doing the prequantization. This is the part I've not discussed about, but that choosing the different prequantization sort of gives you a whole bunch of Morita equivalents at the level of sister algebra are more or less like the Morita equivalents that you have when you study quantum tori. I mean, they can also change the theta in the same way that you can change the theta with the quantum tori.
So going back
with these rational equivalences, I mean a theta plus b mod c theta plus d, something like with a b c d and integer SL2 matrix.
So if you could go back to the slide before this, the general slide with M and the n pairs, or I guess one more before that. The yeah, this slide. Yeah, so the comments from Karen. Yeah.
Constraints over commutative guy will give you a twisted groupoid over a group.
The twisting of the groupoid is related. It comes from the line. Okay.
Exactly, and you get the twist coming from the line by exactly.
Okay. So
okay.
Sorry for the chaos in while they came to check my water counter, so I have to.
So I guess, like, coming back to this slide, like, I'm curious if like Cohn and Dubois-Violette have a paper where they give this sort of cute construction of these theta deformations in terms of what they call splitting homomorphism, where basically replace M with C infinity of M, replace T to the K with the corresponding non-commutative torus, and then do the corresponding things, and then up to isomorphism you do get that theta deformation of M. So I'm wondering if there's a set of choices that you can make so that in general the resulting groupoid C-star algebra is the theta deformation on the nose, or is that too much to hope for?
No, I don't think it's too much to hope for. I think in principle this could be done, but
okay.
Yeah. Because here, yes, I mean, you see it here at the Poisson level. The way in which you're building this thing is actually by you're quantizing the torus, and then you're sort of using the action to move the quantization on M in a way. So that's the same that you're doing in the Poisson level. You're putting a sympletic structure on the torus, and then you're using the action to promote it to a Poisson structure on the manifold. So I think that, yeah, I believe that in principle, yes.
Okay. Thank you very much.
Thank you.
Okay, do we have any more questions?
Yeah, I'll ask the question. I'm curious to see what happens for the higher order projective space. I mean, do you have still that many copies of the compacts?
You have these n+1 copies of compact operators.
n+1 copies of the compact.
Yes.
And for the higher flags.
And then you have this sort of weird, let's say, triangular structure. So let's say in 6 dimensions, you have 3 copies of S5 that are glued together along 2 copies of S3 that are glued together along a copy of S1.
Okay.
And something like this goes on. I mean, some sort of, and this, you can understand it very nicely from this point of view. If you consider the Poisson structure on SUN, or SUN+1, I mean, as you wish, you can plug in as Poisson-Lie subgroups SUN-1, SUN-2, and so on in a triangular order, let's say as upper left corners, okay? When you mod out by a coisotropic, the coisotropic subgroup is sort of twisted. It's not just you're modding out this. So you can mod out with this, you can go and look when you twist the coisotropic subgroup, twist the subgroup to a coisotropic one and then project. Then you can intersect this coisotropic subgroup with all these Poisson subgroups, and they all will project to Poisson submanifolds. So you can take sort of these triangular inclusions of the Poisson subgroups is reflected in this Poisson structure. But of course, you can also consider the Poisson subgroup growing from the lower right corners. Or you can consider SUK times SUN minus K. And all this structure of Poisson subgroups that are all modded out by the coisotropic reflects into different Poisson submanifold. And all this is the reason for all these copies of odd dimensional spheres appearing as Poisson submanifold of your complex projective space, of standard Poisson spheres appearing as well.
Okay. Very nice, very nice. And I wonder, a more naive question, can the quantization process be applied to vector models?
Sorry, the quantization?
could a quantization process, so you quantize the functions on the space, could you quantize vector bundles, quantize projective modules over these things?
Honest answer, I don't know. So I thought a little bit about it, but I was not able personally to come to any specific conclusion from this point of view. I still do not have a very clear idea on what at the Poisson level the vector bundle should be replaced by, because the definition of what is called Poisson vector bundle is a bit too strong. This corresponds to what is called a flat contravariant connection. So maybe you should consider contravariant connections which are non-flat. And not many results that I know of about how to relate properties of the underlying Poisson manifold with contravariant connection on vector bundles over the symplectic groupoid. But possibly it's just that something I do not know. I think it's an interesting remark and question.
Okay, thank you.
You're welcome.
Okay, is there any other question? I see raised hand from Barmir.
Yeah, I have just a very cheap and probably stupid follow-up comment on this last discussion. So this slide that's up here, this is probably just my only défis and limitations, but I would guess that you could possibly get a cute toy model for quantization of vector bundles by considering, by looking at the theta deformation from the very precisely from the groupoid standpoint, and then seeing what theta deformation of equivariant vector torus equivariant vector bundles looks like from this groupoid perspective. It might be quite limited because it is so nice and so special in so many ways, but it's something, I suppose.
Yeah, I believe it could be an interesting approach. I agree.
All right, any more question? And I see there is then from Branimir, but I guess it was from the question before. All right, in this case, let's thank Nicola again.
Thank you to you all.
And yeah, Karen is going to make the announcement for next week's seminar. Or am I going to do it? I don't know. Okay.
You should do it, yeah.
I should do it, okay. So next week seminar, next week's seminar will be from Amaury Freslon from University of Paris.
Ciao, ciao.
Yeah, I hope we will see you again next week.
Hey, Nicola.
Ciao, Rita.
Ciao. I made it when you were almost half through your talk. So
Thanks.
it was a bit challenging.
I guess so.
So I wanted also to talk to